So last time I did not discuss this slide. This is a new slide. One of the things 802.11e did was add a field to the Mac frame. So they added QoS control field, which was not there before. Obviously it was not there because there was no QoS. But now if you have QoS, every frame has to tell what queue it is using, right? And everything else has to say what queue I want to transmit. You know, when you do RTS, CTS, etc., everything has to have this field. So the previous fields are all as before, but there is one new field called QoS control. And the main thing is to know that there is an extra field. So when you see the next time 802.11 frame, or if you trace some of these frames on some kind of monitor, then you will see this field and you will say where it came from. So this is a new field, and this is the format of the field. I will describe the format of the field, but really it's a detail that we can even live without. That's not important. Important part is that there is a QoS field. So the first, basically this is a 2-byte, 16-bit, and the first 4 bits are TID, traffic identifier, which basically says what priority I am running at. This frame is at, okay? And you could have up to 8 priorities, 4 queues. And so 0 through 7 is really your priority, but the number is 4-bit. This is 4 bits. So why they need 4 bits is because you could negotiate something special with the access point. You could say, well, I need this delay, I need this throughput, this and that. So that is called a traffic spec, T-spec, traffic specification. So whatever you negotiated with the access point, and there is a whole set of frames to negotiate that. So management frames where you tell access point, oh, I need this spec, and then they say, okay, you get this. So there are traffic spec numbers, and you can give the number 8 through 15. So when you send the frame, you can say, well, this is going on traffic spec number 8. So whenever the number is more than 7, we know that this is not a priority. This is a traffic spec. Yeah.
Give an example of what one would be.
Okay, so actually the traffic spec comes from differentiated services. Sorry, not differentiated services. I'm just not getting the word right now. But this is from IETF. And the IETF has developed a set of specifications where you have to tell what is your leaky bucket size and things like that. Okay, I mean, so it's a little bit more complicated than just the rate. You can say, well, I will send you 10 megabits per second, but never more than 10 kilobyte. So there is a burst size. Okay, and then there is a rate, and then you pass that through a leaky bucket. And if you send any more than that, then it drops. There is a whole thing about this specification. So an example would be if you're watching a video, and then video is actually very much smooth, but if you have a compressed video, it could be, the rate could vary, right? So you put an average rate, and then you put a burst size, which would be your average frame, somehow, some number of frames that you will say will send. All right, so traffic spec. And so that is the first field is 4 bits. Then there is EOSPU, just 1 bit, end of service period. So what happens is when you go into this APSD, if you remember what is APSD, APSD is that power save thing, right? So unscheduled, UAPSD is unscheduled power save, and I forgot what the D was for. Anyway, delivery, power save delivery. In that mode, basically when you wake up, you send some kind of frame to the access point, say I'm awake, and then they will send you the frames that they have for you, right? So in those frames, there are 2 bits. 1 bit is more bit, which tells you that, okay, next more and more and more, but it may not be able to send, if you have 100 frames, it may not be able to send you all 100 at once, right? So it will send you maybe 10, and it will put this last bit end of service period. Means this time only so much. But if the more bit is on, then next time I will give you more. So there are 2 bits. EOSP says for this period, this is the end, and more bit, which was actually there in the original frame, by the way, more bit was in the original frame. which tells you that there is more frames for you. All right. So EOSP, now you understand. And then the ACK policy. Then since this one introduced block mode, group mode ACK, where you could send 5 frames and get the acknowledgement for 5 frames. So group acknowledgement. So you have to say what is your ACK policy. And that could be that I want every frame to be ACKed. After you send every frame, you will get acknowledgement. Or I don't need any ACK for multicast. Or you could say I want no explicit ACK. So I'm just sending a poll message, please don't acknowledge me, just send me my frames. And our block ACK, which give me at the end of everything, just give me the whole ACK. Alright, so that's the ACK policy. There are 2 bits, so you can indicate these 4 choices. Bit 7 is reserved. Bit 8 through 15 are actually, you can see 8 bits. These 8 bits are to exchange some information, which could be different in different frames. So for example, if it is coming from the access point, and it is a contention-free poll, so that is basically what is used by the access point to say, you are allowed, you are watching a video, and I agreed to give you some frames. Do you have something to send this time? So that is called a contention-free poll. In that, it will tell you the TXOP limit, that this is your transmission limit. If you have something, send me 5 millisecond worth of it. Okay? Otherwise, it could be, for example, a data coming from the access point, or the null coming from access point, or the ACK coming from the access point. In these cases, it would be power safe buffer size, that I can save up to 100 frames. So you know that you don't go to sleep for a year. All right? I won't be able to save it. So that is just the indication from the access point. Now, why does it go in every frame? Because that is actually not the total buffer size. This is the buffer size that is available to me right now. All right? Some other people are sleeping. They have used it, so that is subtracted from here. This is available right now. Third is, if the data frame sent by the non-access point stations, that is normal stations, then if this bit is 0, then it is, I want so much duration. So I really want to transmit for 5 milliseconds. Okay? And if it is 1, that means I have a queue of so many frames. All right? So you can ask in either one of these 2 ways, either the queue size or by the duration. All right? And you can see how they are used. So this 16-bit field was added by 11E. All right? Any question about this field? Yeah. Okay.
The first one, the TXOP limit is the response to the third one, the duration requested, right?
No and yes. Let me just tell you first of all what that limit is. So basically, when the access point sends out a beacon, right after beacon there is a contention-free period. In the contention-free period, you are pre-allocated. So you are given 10 megabits, for example, right? But you may not have 10 megabit at that time. So it will say, do you have something to send? So that is the limit at that time. So the station has not said anything yet, at least in that service period. It might have said, when it negotiated that, okay, I need so much. But this is unsolicited. You understand that? Okay, now, this could also be in this one. So suppose you request this and then you get it. Next time it will tell you what you got. Yeah. Your question.
Yeah, when it says bit 4 and then says EOSP or 0 or 1, does EOSP mean either 0 or 1?
No, actually what it is they are reusing that bit for 2 different purposes. Here it doesn't mean end of service period. Right? Here it could be 0 or 1 or 0 or 1 in either case. 1 means end and 0 means not end. Right? But here that meaning is not there. You just, I mean, sometimes the designers are really crazy about the bit, sometimes they're not. Here they're really crazy about the bit. There's no name for even that 0 and 1. It's just frame type. Any other question? All right, so now that we understand one field, we go back to 11n, and actually we had, I think, finished this slide, so we'll just explain some of the work that we had done on 11n. First of all, I mean, we know that 11n does MIMO, diversity, beam forming, MIMO power save. MIMO power save is that you turn off some antennas. Frame aggregation, you send many frames at once, not at once, you send many frames inside a frame. That is aggregation. It's the opposite of fragmentation. You have you use FECs which are 5 by 6 instead of 3 by 4 for the first time. You use reduced guard interval, reduced interframe spacing, and so on and so forth, right? And you have dual band. You can use either 2.4 or 5.8. Then there is a special coding called space-time block code, which I will explain. Channel bonding is that you can use 2 channels, so 40 megahertz. And then if you use 2 channels, you can even get more carriers out of them. With 20, actually, you get 52 plus 4. Actually, so you are getting, instead of 48 plus 4, which was in A and G, you are getting 52 plus 4, which is at least 10% more. And then when you go to 40, you get more than twice. You see, instead of 52, 104, you get 108. Right? So if you do all that, as we said, you get up to 600 megabits, and that's basically the selling point of N. So I'm going to explain some of the things that we discussed there before. And so first thing is the guard interval. So because there is a multipath, the symbols are coming at different time, and there could be, remember that cartoon about fat people? The symbols could overlap, right? So what you do is you measure, you guess how much is the maximum path delay, or we call it delay spread, and then you say, well, I want to save myself from that trouble, so I will keep the gap between the symbols some amount, right? So they assume that it should be 4 times the spread. Everybody knows the delay spread. Basically, if I get one directly and one through reflection, what is the difference? That is the spread, right? So we want to do 4 times the spread, and they said, well, in a room of this size, the delay spread cannot be more than 200 microseconds, or 200 nanoseconds. Actually, they said 50 nanoseconds in a normal room. I mean, of course, in a big hall, it will be different. Outside, it will be even bigger, right? So for the design purposes, they assumed it would be 200 nanosecond when they designed 11A in 1999. And so they did 4 times that, is 800 nanosecond is the gap. That is called the guard interval between the symbols. Okay? But after it was deployed, they found out that in most places it's a waste of time, because most places 50 nanosecond and not 200. So they said, oh, well, we really don't need 800 nanoseconds. We can just do with 400 nanoseconds. So if you have each 3200 nanosecond of data, and it's the 400 to 800 makes a big difference. 11% overhead you save. All right. So they introduced this new thing, which is reduced guard interval. A and G will use, A, G, and B actually will use the guard interval of, I don't know, for B it matters. For A and G it matters, because when you use this OFDM, then multipath basically. So anyway, so the thing is here, they use 800 and N started using 400. That's the point. Okay? Because most of the, here's another thing too, is because with all these 600 megabits, you're not going to go to Germany, you're just going to go very small rooms. It's not going to go very far. Right? And so with all these high QAM values and everything else, the distance comes down. And so that was another reason. So we are now at 400 nanosecond guard interval. That assumes 100 nanosecond of maximum delay spread.
So this
Yeah.
is just the sum of the interference between two data
Symbols.
symbols. What about the symbols in one data?
What about?
The interference of symbols in one data, the from part.
Interference of symbols in one data. No, so hold on. So you don't interfere with yourself for sure. I mean, you can have either inter-carrier interference or inter-symbol interference. Right?
Each data.
Each data inter-symbol means, okay, let me see. Let me see. So you started the symbol which was this big, right? By the time it came to you, you got 5 copies of this, and that's how it became this big, because 1 copy, 2nd copy, 3rd copy, 4th copy. So that is actually, now let me see. Even though it is the copy of yourself, so you can call it, symbol interference, but really we call it inter-symbol interference because, I mean, it just became big, and then if there is nothing else, if the second symbol was not there, there is no problem with 4 copies of yourself. Everybody remembers that cartoon, and then if you send 1 pulse, then it becomes 4 pulses, kind of thing, right? So if you get 4 pulses, that's not a problem. It's just that if your 4 pulses overlap with with the 4 pulses of the next symbol.
So we are talking about reception, so multi-path reception.
Yeah.
And what he's talking about is transmission to the other side. You are sending your signal. So you're receiving your own signal to the device itself.
Yeah, okay. Now, let's see what you may be saying. What you are saying is that it is quite possible that, okay, it is not an impulse, it's wide data bit sequence, and then that data bit sequence, some sequence bits might interfere with your other bits, overlapping. Yeah, so that will be protected by FEC. So basically, there are ways of even taking care of that, which at some point when we come to that issue we'll talk about. But that is what FEC is designed, so that 1 or 2 bits and errors can be fixed. All right, coding. So White Tarok at Harvard actually invented a new method of coding, and the method is called space-time block codes. Now let me first explain how it works. Is that you could have, instead of 1 antenna, you could have 2 antennas transmitting. So you have these 2 antennas, antenna 1 and antenna 2. This is what we call a space. And you could have 3, 4, 5, 6 antennas. So that is your space. And then what you do in time, which is vertical in this matrix, is that on the first antenna you send S1, on the second antenna you send S2. First symbol and second symbol. But right after that in time, second time slot, in the first antenna you send minus S2 star. Okay? And on the second antenna you send S1 star. If you do that, what is a star? Star is the complex conjugate. So if this is S complex conjugate X plus IY, the conjugate is X minus IY. Okay? In terms of phase, it is just, you can see in this phase diagram that if it is here, you just take the mirror of it, and that is your complex conjugate. Right? So many of you have done this complex arithmetic. I don't know if somebody doesn't know, but basically this is I is the square root of minus 1. And so if you, so this one is S1 star, this is minus S2 star. And if you do this, so you see you are sending 2 symbols in 2 slots. So your rate is 1 symbol per time slot. So this is rate 1 coding. Basically, you are not really gaining anything, you are not losing anything. But you have 2 antennas and you can send 2 symbols, but you are sending only basically 2 symbols in 2 time slots. Alright? With this, what happens is that these things are orthogonal. These 2 signals are orthogonal. If you multiply them, S1, S2 minus S1 star, S2 star, they turn out to be 0. Okay? You have to basically, so anyway, so they are orthogonal, and therefore it is much easier to get to basically estimate the channel, and you can get much better data rate. I mean, basically you can get rid of the noise much better. And so these codes have become basically standard since 1998 basically. So every technology since then uses this. Yeah, go ahead.
What is exactly being sent in S1 and S2?
What is exactly? Okay, so S1 is a symbol. So if you remember, I think we had a picture here. So this 00 is a symbol, right?
Is it one
Huh?
chunk, or is it an entire block?
So basically it depends upon the, it is the modulator size. So 4 QAM will only take 2 bits.
Okay.
If you had 256 QAM, then you will take how many bits? 2 raised to what number is 256? Okay, 8. So you will take 8 bits. 6 is 64 and 4 is 16 and all that, right? 2 raised to powers of 2 you have to remember. So here 4 QAM is 2 raised to 2. So it will take 2 bits at a time. And if it was 256 QAM, it will take 8 bits at a time. So that is the symbol. Right? Basically what happens is this symbol is a dot. Remember in that whole coding scheme, if you remember the QAM, basically you have to draw either 4 dots or 16 dots or 64 dots. So the symbol is a dot, and then you take the conjugate of that, which is the mirror image of that symbol, and you send that. All right. Now, so let's see. So you precisely coordinate the distribution symbols and space and time, and the receiver combines the multiple copies of the signals. And now if you do all the mathematics which they do, then you can basically get a much better idea of the channel and much better signal you can filter out, noise you can filter out. Okay, even though your rate did not go up, but with 2 antennas, now you have much better possibility of getting without error. So this is called space-time block codes. Now, the example that I have given here is 2 antennas, but obviously it is not limited to 2 antennas. Channel bonding. So you can take any 220 megahertz adjacent channel. So you cannot take one channel here and one channel there. They have to be next to each other, and you can make a 40 megahertz channel. And now it becomes very clear as to what happens to channel 5. So if you do 20 megahertz, you can take channel 1, which in G will mean 1, 2, 3, 4. 5 megahertz times 4 is 20 megahertz. Right? But for N, you need to combine 2 channels. Either you take this complete plus 5, 6, 7, 8, 9, or you take this complete and you take 2, 3, 4, 5. You see? So they have to be 20 megahertz adjacent, and not with a gap in before, like before we had. So basically we were leaving out that channel 5 unused so far. Okay, so that is one little detail you have to know, is that 40 megahertz is contiguous, and therefore if you start at 2, you end it here. And you don't have to start at 2, you could start at 3, 4, 5, those are all legal values. It's just that people just try to keep it so that other people will use it. So I mean, you don't want to, if you start in the middle here, you might overlap everything. Right? That's why we start at 1 or 2, because that way at least the overlap with other people is minimal. Alright. So OFDM, when you want to do OFDM, we already said that you get 52. How do you get 52? Because you use on the guard. Previously we had 6 guards on both sides, carriers, right? Now we do only 4, so we get 48, 4. So we get 2 more actually on each side. So 4 total carrier more in 20 megahertz. In 40 megahertz, we don't have to have that guard, and at least in the middle, and so you have 108 data channels. So basically, you see from 48 to 108, 48 to 108 is more than factor of 2, 96 plus 12. So with 40 megahertz, you get more than factor of 2. Now, one of these channels you have to call primary, and one of these channels you have to call secondary. Why? Because some people may not be able to use 40 megahertz. So I have this 11N base station, but you can have 40, and this person, even though it speaks 11N, doesn't speak 40. Right? So we have to be able to send to both of them all the time. That means every frame has to decide whether it goes on 40 or goes on 20. Every frame. It's not that we just divide the whole network uses 40. Whole network cannot use 40 because the whole network is not one thing, right? Every station buyer decides what station bit they want to pay for. And therefore, there is one channel which is common, 20 megahertz, which everybody listens on. That is where we say, okay, all right, I want to transmit 40 megahertz for 20 microseconds. Right? And then, when you transmit, if nobody else complains, you get a clear signal and you can send it. So even though you are using 40, you have a one primary, which is 20. Yeah.
Heterogeneous wireless networks, will this still work with OFDMA?
Okay. I don't think they're using OFDMA here. OFDMA will come in WiMAX. When we go to WiMAX, there they use OFDMA. Here I think it is just plain you get all the carriers. So when you transmit all 108 carriers. Okay? So we don't do here that 2 users can transmit, you can transmit 54, you can transmit 54, we don't do that. That can be done, but that is done in WiMAX. So here there is no carrier allocation, it's just the whole thing is allocated. But we do choose between 40 and 80, 20 and 40. Alright, so you understood how 40 megahertz comes, that you don't use complete channel 1 and 6 together. You see something is left here because they have to be contiguous. Alright. By the way, there is a reference here which is really the recommended reading, and actually I have become a fan of this guy. So I would recommend that you read all his books. And so he writes well. Frame aggregation. Now you have to differentiate between frame bursting and frame aggregation. So frame bursting is that you send a frame and 802.11e. 11e allows you to send a burst. Right? And you can get the acknowledgement for those. So you send, let's say here 6 frames and you get the acknowledgement for 6. Those are 6 MAC frames. Send on 5 frames. But if your SDU was very big, service data unit, which is actually the IP packet, which is given to the wireless, if this IP packet was very big, then you will get only fragments. You will send part of it here, part of it here, part of it here. So that is what we call fragmentation. The opposite of fragmentation is aggregation. Aggregation is that if you get very small IP packets, right, instead of putting header on each of them, you just put them into one big frame. Alright, so this whole thing is one PDU. Alright, so you understand the difference between aggregation and bursting? In bursting, every PDU has a header and and so on and so forth. Here there is only one header. Of course, there is some extra bits here which says how long is each SDU so that it can be broken up later on. So, but there is one MAC header. Alright, and you can combine. Interesting thing is you can combine all of these or 2 of these. So how can you have bursting with aggregation? Can you think about how can you have aggregation with bursting? Can you do both? Right, you have lots of tiny stuff, put them into a PDU and take lots of PDUs and send them one after another. Right? Of course, fragmentation can be done same way. Do the fragmentation and then put them in a burst. Or you could have some tiny stuff, some big stuff, something is fragmented, something is aggregated, put them into PDUs, right? So everything is all independent. Any question about this? So in 11N, there is a special bit pattern that you have to put when you aggregate and do things like that. So this is your IP packet. If you are going to put that inside a frame, you have to put some kind of delimiter at the beginning, at the end, to make it a subframe, and then you put it inside a PDU. So this is actually aggregated MSDU. So what we did was we took this is an SDU. This IP frame is what we call a service data unit for Mac, MSDU. We put these headers and trailers, and then we put many of them together. So this is the aggregation, and this whole thing is called AMSDU. Now this whole AMSDU becomes one PDU, but if you want to put many of these PDUs in the A5 frame, now this is another thing, right? So you take this whole thing, put the limiter and the padding, and this becomes part of this whole PPDU, right? So this is called aggregated MPDU, because generally a PPDU consists of a header and then a MPDU, a MAC protocol data unit. So we do have one MAC protocol data unit, but it has many protocol data units inside it. And therefore this is called AMPDU. And this could also be called PSDU. File layer or PLCP SDU. Alright. So now we introduce 2 new terms, AMSDU and AMPDU. AMSDU consists of many MSDUs, right? AMPDU consists of many MPDUs, but it looks like one. Clear? Okay, moving on. So now the MAC frame has an extra field. 11N added an extra field in the MAC frame. So the QS field is already there from 11E, but there is another field from this one. And again, this is required because we have MIMO. Because we have MIMO, because we have STBC, etc., etc., what we need to do is we need to estimate the channel. And we need to, basically figure out, so to estimate the channel, what we do is you send something and you ask the receiver, what did you get? Did you get lots of errors? Oh, I sent a 256, you got a lot of errors, so I'm going to reduce 64. Did you still get an error? Oh, you got it, I'll go down to 16. So you do that kind of thing, asking the receiver and receiver giving you feedback. Yeah, this sounds good. Now I can hear you well. All right, let's just stay here, okay? So that's the kind of thing we do, is that we get the feedback from the receiver. So that is what is done by these fields. And so this is called high throughput control field, which is 32-bit long. And in this 32-bit long, 16-bit is what is called link adaptation. Then there is a calibration, and then there is a CSI, NDP, and all that. I'm going to explain that in a minute again. Not that it is critical for you to know, but at least now that I prepared this slide, we can just go through that once for sure. It's a little bit more detailed than we would have gone, but it's okay now. And then this 16-bit consists of fields like this. So one thing which sounded strange to me is that 11N guys want to squeeze out every single bit and byte. So they said that first time when you transmit, there's no need for you to draw a random number. And this is something strange to me. I got to verify from the standard, because I read this in the book, but you never know, sometimes these things could be wrong. So first time you just use SIF. So you see the channel is idle, you want to send, and then so you use, instead of diffs, you just use SIF, smallest value. And then, so that way it will have priority over ABG, which is kind of unfair. So ABG guys will have to wait for diffs, but 11N. But this is, okay. The point here is for the ST control. So ST control is for channel information, and then you have to now again read the next slide and this slide together. Picture slide, or we can just go to the next slide and come back, flip and back and forth. So TRQ is the training request. Training request means please send me a sounding PPDU. All that means is please send me something that we both know so I can figure out what is the error rate. All right. MAI, the next field there, MAI is MCS request or antenna selection indication. So there are different functions, totally different functions, which are combined into this M and A. I is the indication. When this number is 14, now how long is this MAI? MAI is 4 bits. So it can be from 0 through 15. When this number is 14, then the feedback field, MFB, which is the feedback field, contains antenna selection indication that I selected antenna number 3. So you can figure out, basically for all the antennas, right? Antenna selection indication. Otherwise, it is the MCS request ID. Otherwise, it is the modulation and coding that I want you to use coding number. So all the codings are numbered from 1 through 127 or something like that. So say I want coding number 33. 33 might mean that we are going to use 64 QAM with 3/4 rate, right? So the combination of FEC and QAM is MCS, modulation coding scheme, and they have a number. Rather than saying 64 QAM, they just have a number, right? So that number is put that I want you to send it this one. MFB is the feedback, and then this is the sequence identifier. And that basically is the sequence number that, you might have sent me request number 5. So here is the response to request number 5. This is the response to request number 6. Sequence identifier. Antenna selection command or data. So, basically I want you to select antenna number 3. Calibration. So there is a bit here for, there are 2 bits for position and 2 bits for sequence for the calibration. So the first 2 bits identify the calibration sequence that, when you are doing the calibration, every time we increment from 0 through 1, 2, 3, like that. And second 2 bits identify the position of the calibration sounding exchange. So there is a whole set of types of frames which are sent in the calibration time, and so this is basically identifies that. So it says 00 is not a calibration frame, 01 is a calibration start, sounding response, and sounding complete. Now you don't have to remember all these numbers, I don't remember either, but in general you have to know that basically a lot of things goes on before we select how we can talk to each other. Okay, because there is so much choice, but there are so many variables in terms of noise and delays and so on and so forth. So you need these calibration, antenna selection, sounding, and all that. CSI, channel state information steering. So they exchange the matrix. So they say, okay, I got your thing, your space-time block, whatever, and then here is what I think the channel looks like. Here's the matrix. Okay. Now that matrix you could send it compressed, uncompressed. If you send it compressed, there is a number, and if uncompressed, there is a number, and this might be some kind of other information about the same matrix. Okay. NDP is null data packet announcement, and this is basically a sounding packet. This is basically a packet which does not really have any information, but this you can just send it, and so that is this one is an announcement. This one is just a 1 bit, but after this header, a null data will follow. Access point constraint. So this one basically says that you can only respond to this with the same traffic ID as the last one. If this bit is 1, means that if I send you priority number 5, this is same priority number 5. 0 means you can send anything. RDG is reverse direction grant is present. Basically that means that I am also giving you permission to send me some more. Reverse direction grant is that I am giving you permission to send me 5 packets. So anyway, so the idea is, I think this is it, yeah. So the idea is there is a field here which is used for estimating the channel and for basically exchanging some information about what you can send to the access point. Okay, this was not there in anything before N, but N added that, and of course the rest of all the following standards are using this, which we'll see in a minute later on. All right, now so the major point is that there is a lot of calibration, and that you have to remember, that's all, and not so much detail about each bit and byte there. All right, that actually finishes the 11N, and we are on to 11AC. Any question about 11N? Okay, so we talked about channel bonding, we talked about guard interval, we talked about primary channel, etc., right? So now we are going to go to the latest. Now 11AC went in every direction where 11N went 2 steps ahead, right? So now they allow up to 160 megahertz channel. You can use 80 and you can use 280. Obviously you cannot find 280 next to each other, so they allow 280 anywhere. So that's why you call 80 plus 80. You could have 80 here and 80 there. So that non-contiguous. Obviously you cannot find 160 or 80 in 2.4 gigahertz, so this doesn't run at 2.4 gigahertz. Because if you ran at 2.4 gigahertz, you will just swamp everybody else. Your phone will stop working. So So basically, this runs only at 5 gigahertz, where there is plenty of channels to do this kind of things. And in 11N, we had limited to 64 QAM. AC goes to 256. So just by doing that, you get 8 by 6, 8 bits versus 6 bits per symbol. Eight spatial stream. Now remember, in 11, and anybody remembers what is the maximum number of antennas? We had some numbers there, 2 by 2 colon 2. Anybody remember the highest? 4 times 4 times colon 4. Here it is 8. Well, it is not the number of antennas, it is the number of streams. Means that you remember what is the difference between the stream and the antenna? What is the difference?
You could set the minimum number of streams, and if you have 2 transmitter and 4 receivers, then you will be able to send only 2.
There is no point in sending more, and second thing, you need hardware for the streams to process the streams. So you could have antennas, but then you don't want to pay for the amplifiers and things like that. So that is all. Streams requires hardware inside, right? So it allows you up to 8 streams. So you can get 2x right there. And then it allows multi-user MIMO. And that requires explanation, so hold on to that thought. Null data packet, explicit beamforming only. Now, this is where they're restricted. So in 11N, they had many different ways of finding the channel and doing this thing. And everybody implemented differently and they got into trouble. Right? So here in 11AC, there is only one way to do channel estimation and beamforming, and that is that null data packet. And you know what is null data packet means? Just a packet which has no data and is sent so that we can figure out what's going on in the channel. And they want to squeeze out every carrier, so they have less pilots, means more data. So we have 52 plus 4 in 20 megahertz, 108 plus 6 in 40 megahertz. I think these numbers are same as 11N. But this number goes up. You see, when you go from 40 to 80, 108 would be 216. But again, you get more. And when you go from 80 to 160, you get 468, which is more. So interesting thing is that when you go from 20 to 160, you only use 8 times more bandwidth, but you get 9 times more throughput. This you have to remember, right? I mean, you cannot remember many of the other things, but this you have to remember, that with 8 times bandwidth, you get 9 times more throughput. How? By having more data carriers and not having as many pilots. And guard band. All right, and there are some MAC enhancements. So if you just do one stream at 20 megabits and short GI, guard interval, so that 400 nanosecond is here, 20 megahertz, one stream, you get 96.3 megabits with one stream. Right? This is where we were getting 54 megabits with 11G. 54 megabits. Actually, there was no short GI, but with one stream, 20 megahertz, 11G and A give you how much? 54. Here we get almost twice as much, 96. And then obviously if you do 8 streams, you get 9 and 8 times the bandwidth. So you have 8 times the bandwidth, 9 times that, and 8 streams, 8 times that, so 8 times 9, 72 times of 96, you get 6.9 gigabits. So this is like 10 gigabit Ethernet, right? 6.9 gigabit. Actually, one thing I didn't tell you last time, that the marketing people are very smart. When Ethernet 11N gives you how much? 600 megabits. In gigabits, how many gigabits is that? 0.6. But if you have to round up in one digit, how much is that? 0.6 is rounded to 1. So that's a gigabit network. All right? That's a gigabit link. This one is 10 gigabit link. And in fact, you believe it or not, this was discussed in the standards. I mean, when we were doing 10 gigabit standard, 10 gigabit Ethernet, people were not sure whether 600 megabit is good enough or not. Because they had a design for 600 megabit, and that could have been just called 10 gigabit and done. But some people stuck to the point and said, no, 10 has to be 10.00, not 0.6.93. So anyway, so this is the kind of thing that is done in the marketing anyway. So this is 6.93. Now you see how fast suddenly now we can run 6.93. Of course, you cannot run it right now today because it's very difficult to find equipment which is this and blah blah blah. But this is it will come in waves, maybe in a year or two. You'll get it. And now you understand how they get it. First of all, the one way to increase the bandwidth is to increase the data rate is to increase the bandwidth. Second thing is to increase the QAM part, go up and up in QAM, right? Modulation. And then the rest of it is noise. Okay? Now, so AC has a frame format which is different from 11N. They still use that HT control field, but the first bit which was reserved is now 1, and therefore it is VHT, very high throughput. So this format is totally different than the 11N. Look at the first bit. If the first bit is 0, then it is 11N. If the first bit is 1, then it is 11AC. Okay? Now again there are some bits here which we'll discuss, but they are practically the same way like 11N. MRQ is the MCS feedback request. RQ is request. So please tell me how am I doing in 256 gigabit. I'm going at 256 whatever. QAM, is it good enough for you? MRQ sequence identifier, MRS, is basically tells you that this is answer to your question number 5 and now answer to question number 6. So you could keep asking many times and then the answer comes back. You have to have a number with it. So that is sequence ID number. STBC is space-time block code I'm using. MFB is the feedback, and MFS is the feedback sequence number. So this is the answer number. That was a question number. MRS is your question number. MFS is the answer number, which generally should be the same as the question number, but the question and the answer can overlap, right? So MRS, set to MRS for solicited MFB, and there is unsolicited feedback. Sometimes I'm just going crazy. I want to tell you, look, I can't hear anything you're saying. All right, so I send you a feedback. Right? That is unsolicited feedback. All right. Now unsolicited feedback. Now again they're reusing the bits. So you see these 3 bits are used for group ID. Group ID is 6 bit long. 3 bits are here and 3 bits are here. Group ID low and group ID high. Now these 3 bits can be used for group ID, but when not being used for group ID, that can be MFS. So this can be used because both of them cannot be at the same time. So it could be either MFS or group ID. This is like ESOP. Remember that 0-1 thing? Here they are reusing those 3 bits for 2 different things. It is either MFS or it is group ID. So unsolicited feedback. So I am sending you this because you didn't ask for it, and therefore this bit will be set to 1. And that is this 1 bit, unsolicited MFB. When this bit is set to 1 means this is you didn't ask for it. And then I have to tell you, since this you didn't ask for it, that this is a feedback type for unbeamformed or beamformed feedback, and whether it is for which kind of coding, LDPC or BCC, there are 2 kinds of coding, and group ID is basically the group ID of the PPDU, the block number of the PPDU that the feedback is about. Anyway, so there is, the idea here is that the feedback can be requested or feedback can be given without request. Okay, when you give it without request, you will tell, what is it that where you got into trouble. And then AC is the access point constraint, which means that I'm requesting, this is generally used when you're requesting something and you say, well, just any traffic ID or traffic ID same as the last one, and RDG is the same, reverse duration grant, just like in 11N. Alright, so this is a new frame format. AC and RDG bits are same as before, but I think many of these things are different. And so the same length, 32-bit. It is still called HT control field, but it is BHT. Any question about this? If not, then we move on to beam farming. So what is beam farming? Beam farming basically means that we can direct energy towards the receiver, directional antenna, right? And the beam farming is not just directional. Directional could be just static. On the day 1 when you install the antenna, you just direct it to the moon, or to the satellite. That is not beam farming. That is directional antenna, right? Beam farming is when you can electronically steer the antenna, electronically move the direction by the microseconds. So that is why it is called smart antenna and antenna array. Now implicit means that the channel estimation using packet loss, and explicit means the transmitter and receiver collaborate. So there are 2 kinds of beam farming, implicit and explicit. Explicit is that, okay, now let's decide whether my direction is correct or not. So how much do you hear? 2 decibel. Okay, I'm going to change a little bit. How much do you hear? 3 decibels. Okay, fine. I think they're, now I'm aligned to you. So if the receiver helps you, then you can really figure it out much better. That is explicit beam farming. Implicit is, you get lots of errors and you get lots of, not acknowledgement missings and things like that. Then you figure out, I think I may not be aligned. Things like that, right? So, forget about the require part. But anyway, so the explicit requires the feedback, and that's why you need those sounding frames and things like that, those feedback request and feedback sent and all that, right? Now, multi-user MIMO. This is a new concept with 11AC. Actually, this was all done with WiMAX, but now used in 11AC. Is that one problem with MIMO is that the antennas, when you have 2 antennas, they cannot be just anywhere. They have to be properly aligned. And they have to be aligned by lambda by 4 or multiple of it, right? Some multiples, and there are some positions. Anyway, lambda, so because here, if you have 2 antennas and you send a sine wave from this and sine wave from this, if they are misaligned, it is quite possible that the 2 sine waves cancel out, particularly if they are half wavelength away. Right? So quarter wavelength is what you need. Now how much is the wavelength at 2.4 gigahertz? 12 centimeters, remember? So 1/4 of that is 3 centimeters. So 2 antennas should be 3 centimeters away. Now 3 centimeters is probably okay, but if I add 8 antennas, I can't do it on this phone. Right? And so many places you cannot use many antennas simply because there is not enough space. So what can you do? So somebody came up with this nice idea that really you don't need to have all the antennas in one device. You could have different devices of antennas. So for example, this could be user 1, this could be user 2. Each of them have one antenna, but they could work like as if there were two antennas. Multi-user MIMO. So basically with this two antenna, we could still do MIMO, still get twice the bandwidth, and basically we could send on the same frequency at the same time to do two different users. So we are reusing the same frequency, exactly the same frequency, exactly the same time to two different users. It's just like MIMO. In MIMO, what we do is we do two streams, but they are independent in some sense so that you get twice the data rate. But here, they are not going to the same people, they are going to two different people. And the interesting part is that those two people don't even know that they are doing this, that they are helping out each other. Huh? Yeah, right. So that's actually, so I'm just going to explain briefly, but that's a whole book, right? Book on MIMO. But I'm just going to explain briefly. So if you remember the way OFDM works is that you have frequency on one axis and the time on the other axis, and to different users you give different frequencies at different times, right? And this picture actually came from WiMAX days, and when I was working on WiMAX. So it may not apply to 11AC, but the way it was done in WiMAX, this multi-user MIMO, was that you have two pilot positions, P, 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 P. Now these carry well-known data. So these are used for estimation, channel estimation, to figure out where the data is coming from and what is the rate and all that. So you just use this for estimation. Now what we do is in WiMAX, to user 1 we give these two pilots, to user 2 we give these two pilots. Now both of them use the same frequency and the same data at the same time. So these things are all common. Remember, vertical axis is the frequency, horizontal axis is the time. Remember OFDM? OFDMA, he said OFDMA. In OFDMA, vertical is the frequency, horizontal is the time. Now, same frequency, this frequency, both users are using the same frequency, but they just have the pilots which are different. Okay? And using that information and doing some mathematics and transforms, they can figure out what this guy is saying and what this guy is saying. Okay? So this is basically a game of what we call channel estimation, to get the channel information by using the pilots correctly. Okay? Now, so with this, what happens is now everybody can have just one antenna and they can benefit from MIMO because the base station can send you to multiple people at the same time. So this is like a switch versus hub. Remember, when we had Ethernet hub, only one person could talk. If two people could talk, they collided. Right? With this switch, everybody can talk at the same time because there is no collision. Right? You know the difference between switch and the hub, right? So same thing here now. With multi-user MIMO, we can make a switch. Access point becomes a switch. Everybody can talk at the same time. Now if you do beam farming, you can do both beam farming and multi-user MIMO. So this one shows all four streams going to one device. This would be beam farming. This one shows beam farming with MIMO. So two streams going there, one stream going there, one stream going there. Now, here's the thing though, one thing you should, I prepared this picture and then I felt that maybe people will get confused from the colors. The colors are confusing because these are not different frequencies, these are same frequency. Okay, this is same channel 1, channel 1, channel 1, channel 1, channel 1. So we are sending 4 streams on channel 1 here. Here we are sending 2 streams, 1 stream and 1 stream. You understand? So on the same frequency, at the same time, we are talking to multiple people. Okay? That, then finally, okay, so one more slide. primary and non-primary channels. So now if you have all these and some people are speaking 20, 40, 60, 80, 90, there is a lot of confusion as to who is speaking where, right? So there is a primary channel here, and the primary basically, so for example here, let's look at this left half. The primary doesn't have to be lower or higher, it could be any one. So here I have shown an example where primary is with 220 megahertz channels, the primary is the lower one. With 240 I have shown that the primary is this higher one. With 80 I have shown the higher one. So it doesn't matter which way it is. So you could have higher or lower, but one of the channels could be primary, other is secondary, I mean non-primary as they call it. So what happens is, primary is where you do the most of the negotiations, and so everybody can hear. So let's say we are doing 40 megahertz and 20 and 20. Some people cannot hear 40, they just hear 20. So they listen on the primary. Right? People who are doing 40, they have to announce on 20, primary one, as to that they want to talk on 40. All right? So, so that way now we can have all these stations supporting different things. So you speak 40, you speak 20, you speak 180, you speak 60. Okay, all right, you just tell me what you speak, but speak in one channel, primary. And then when your turn comes, you use whatever you can use or whatever you are given. All right? So you can mix stations, multi-band stations. Second thing is, another interesting thing is that you can mix multiple networks sharing the same spectrum. So here I have shown on the right side two networks. We can call them green or blue and yellow, whatever. They are using the same 160 megahertz. Same 160 megahertz, not two different ones. All right? How they can share? Because they're not using it all the time. Sometimes they're using 80, sometimes they're using 40, sometimes they're using 20. All right? So when they want to use, basically when they're using 160 will not succeed on this one. If the right one is using, the left one will not be able to use, but in the next microsecond it can use it. So you have to sense the channel right before you use it, whether the whole 160 is available. If you get it, you got it. And the other guy will find it busy. So multiple networks can share the same big channel bandwidth. Yeah.
With the beamforming and the multi-user MIMO, is there a relationship between the antennas and the users? Like one antenna, one user, 5 antennas, 5 users?
Yeah, okay. So that's correct. So, so here's the thing, I mean, the total number of everything cannot exceed the number of antennas. If you want to do 4 things in parallel, you need 4 antennas. Right? Now, 4 antennas cannot give you any more than 4 streams, so you need 4 hardware pieces somewhere if you want to do 4 streams in parallel. Now, those 4 4 streams can be divided any way you want among people. So you can have 2 plus 2, 1 plus 1, or 4 times 1, or 2 times 2. Does that answer a question? Okay. So you are limited by the number of streams and number of antennas. That brings us to the end of this module. Summary, 6 points. First, we know now SDU and PDU. They can be aggregated, fragmented, and bursted. Alright, so bursting is different than fragmentation than aggregation. 11 and G use OFDM with 64 subcarriers. This you have to remember, okay? I mean 20 megahertz, 52 data, 4 pilots and 8 guards. So this 52 number keeps going up. 11E adds the frame bursting, direct link, APSD, right? 4 queues with different AIFS. Now you know what is AIFS and TXOP, transmission opportunities, and QS field in the frames. 11N adds MIMO aggregation, dual band, now it runs on both bands, STBC coding, and then ST control field in the frame. So that is what new came with 11N. 11AC went a step further with multi-user MIMO and 160 gigahertz by having 280 megahertz, and they don't have to be contiguous. Okay, and then 256 QAM, 8 streams to give you 6.9 megabits, and the multi-user MIMO allows several users to be combined in a MIMO pool. Any question about anything? Well, so there are two books from this guy, my favorite guy, M. Gast. He wrote one on 11N, one on 11AC, and that's why I became a fan of him, because both of them are very good, easy to read. There is a book from Cisco on the original other 11 stuff, if you want to know ABG. There are plenty of Wikipedia links and these references if you want to know more about it. Okay?